G'day, Dr. Carl Shirtloads of Science, University of Sydney, here to talk with Professor Sarah, have I got that right?
Yeah, that's right.
Perkins-Kirkpatrick.
Yeah, that's right.
Right. And so you're a professor at ANU of
Climate science.
climate science.
Yes.
I wrote my first story on, I'm not a climate scientist, on climate science in 1981.
Yeah.
Were you born then?
Nope.
No. But you have progressed mightily in this field, and so you are a professor of that. So what's your
Yeah.
official title within the university with ANU?
That's a great question. Just Professor of Climate Science.
Of climate science?
Yeah.
I'm just the gadfly, the little butterfly that knows little bits and pieces, but you're the one who knows so much more.
Thank you.
Well,
I'll take that as a compliment. Yeah.
and so you've been working on many things, including what would the climate look like after we hit net zero. But it's possibly worthwhile, just for people who are not familiar with the history, just to run a little bit through the history. So we go back to, say, Fourier, who was wondering why. Can you take us through that?
Yeah. So we've known about the greenhouse effect, which is what drives our atmosphere to be warmer, for over 200 years now. And Joseph Fourier, who's also famous in the mathematics world.
The Fourier transforms and all that sort of stuff.
Exactly. He kind of noticed that there was something about the atmosphere that meant heat was being trapped in. So he did some basic calculations and realised the Earth should actually have been a lot colder when you consider all of the radiation coming in from the sun and the radiation that comes off the surface of the Earth. There was some imbalance there.
It should have been sub-zero instead of
Yes, exactly.
positive.
Like I think it should have been maybe 30 degrees colder or roughly that amount. So yeah, it was a big difference.
There was something going on.
Yeah.
And then we rolled forward to two scientists around the 1850s. There's Eunice Newton Foote.
Yes,
and
that's
you know,
right.
I cannot find a single photograph or drawing of her.
I thought I found one once, but maybe I didn't. Maybe I'm
There's a picture of somebody with a dog.
And that's not her?
That's not her.
Right,
Apparently I thought
That's
it was
a shame.
her.
Yeah.
Boo the patriarchy.
Yeah,
and then,
yes.
Then on the other side of the Atlantic, John Tyndall. So
Yes.
can you take the audience through what they did?
Yeah. Eunice Foote, she was a amateur scientist, as if you wanted to be a scientist as a woman in the day, that's what you had to be. And she kind of tried to measure whether or not carbon dioxide was a heat-trapping gas. But she kind of did it the wrong way. She kind of did it on at the ground, and she was proposing that carbon dioxide was trapping sunlight coming in, not the long-wave radiation coming off the surface of the Earth.
But you've got to do the first experiment before you can do the second one. So she did the first.
Yeah, so she correctly got something right,
Yeah.
but kind of like Joseph, like something's going on, we're just
Yeah.
not sure what it is. She was able to pinpoint it a little bit more.
Yeah.
And it's important to remember that when the atmosphere heats, it's not the shortwave radiation or the sunlight coming in. That's absorbed by the surface of the Earth, and then that rebounds as long-wave radiation, and then that's what heats our atmosphere. And if we have certain gases in our atmosphere, that's what traps the heat or that long-wave
And we'll come
radiation.
back to that again.
Yeah.
And then also on the other side of the Atlantic, we had John Tyndall.
Yes.
At the Royal Institution.
He was very soon after Eunice, and we've had a discussion whether or not he kind of stole some of Eunice's work. There's no way of proving that because, she published her work in scientific journals but under a pseudonym. So whether or not he knew or that, he was a woman or stealing her science, that remains to be...
So they're heading closer to
Yes.
the concept that carbon dioxide could be a one-way valve, that it would let heat in but not out, but we're getting closer.
Yeah, that's it.
And then we roll forward to Arrhenius.
Arrhenius, yes. So he could actually prove the heat-trapping properties of carbon dioxide. He set up this little experiment. I can't name the instrument, so don't make me. But he set up this experiment and could show that carbon dioxide could absorb certain bands of long-wave radiation. And he did that in a lab, like in an actual scientific
And
lab.
he did a lot of mathematics as well.
Yes, yeah. And he also proposed what we now call the climate sensitivity. So for every doubling of CO2 or carbon dioxide we have in the atmosphere, temperature is meant to rise roughly by 2 or 3 degrees. That was his proposal.
Amazingly accurate.
It is amazingly accurate. Like now we kind of can research, what happens if certain systems change in the climate system as temperatures go up. But he was pretty much bang on the money.
And then we roll forward into the 1930s with Guy Callender.
He basically measured this temperature change. So he used a couple of hundred stations across the world, I think, and basically plotted that temperature was going up. And he went back to Tyndall's work and Arrhenius's work and proposed, here's the proof this is starting to happen.
Beginning to build the picture. But of course,
Exactly.
you must remember that correlation is not causation.
No, that's it.
And the classic example is that in the top right-hand corner of the United States in Massachusetts, the divorce rate is very closely related to the overall daily consumption of chicken across the USA.
So really, I'll have to roll out that statistic at some point.
But he was getting closer. And then we start taking really good measurements on Mauna Kea.
Yeah. So the Keeling curve is something that is still currently running, at least for a little bit longer, perhaps. It's a measurement that's taken at the Mauna Loa Observatory, and it measures how much carbon dioxide we have in the atmosphere. And it goes up annually, basically. There's a seasonal cycle. So it peaks in Northern Hemisphere winter and declines in Northern Hemisphere summer, because that's, the trees are breathing.
Is that because there's more land in the Northern Hemisphere as opposed to the Southern Hemisphere? So there's more trees.
Yes.
And so they predominate in summer. They suck the carbon dioxide out.
Correct.
And in winter.
Yep.
I believe they even got to the stage where they could pick not just the difference between from one year to the next, and not summer to winter, but also month to month and day to day.
Right, okay. I did not know that, but it doesn't surprise me. And we actually have a recording station here in Australia as well from it's called Cape Grim.
In Tasmania.
And it basically verifies what the Mauna Loa, the Keeling curve, says.
Right. And then in 1973, Munich Re, the world's largest reinsurance company, and so they're the big guys. So you might insure your car against being hit by hailstones in your local town, and the Professor Sarah company will take your insurance money, and suddenly you say, but what if this hailstorm comes over and I have to pay out 100 million cars? So then you go to a reinsurance company like Munich Re, and in 1973, Munich Re said that it was quite clear, because of their centuries of insurance payouts and weather records and climate events, that there was a link between the rising carbon dioxide and their insurance payouts. So they started increasing premiums in 1973.
I did not know that. I did not know that at all.
But then other stuff that I don't know, so we sort of fit in.
Yeah.
And then we roll forward to the fossil fuel company, James Black, for Exxon in 1977, saying there's something going on, let's research it. So is it true that from about in the 1980s that the world's best climate science was being done by the fossil fuel companies?
That's a good question. I'm not entirely sure, but they did research. I wouldn't know if it was the best research. A lot of people were starting to sit up and take notice at this time.
And in 1982, they published a curve showing if you did business as usual, in 1982, that by the year 2020, the air temperature would have gone up by about 1 centigrade degree-ish, or 0.8, which is remarkably close. And the carbon dioxide would have been about 415 parts per million, which is remarkable.
Yeah, they pretty much got that.
And then in 1990, two things happened, which was that firstly, the scientists finally had enough data to say, yes, this is real. And the fossil fuel companies said, no, it's not real, and we're going to spend $1 billion a year telling lies like our good friends in tobacco and alcohol.
There's a whole series of books describing the similarities, uncanny similarities between big tobacco and big fossil in the denialism movement.
Naomi Oreskes
what
was her book called?
Merchants of Doubt.
Merchants of Doubt.
Great read.
And then Michael Mann has written a few, The New Climate Wars and so forth.
The hockey stick.
And I've written a little tiny book called Dr. Carl's Little Book of Climate Change Science.
I did not know that. I'll have to look that up.
And are you writing a book on this?
No.
You will.
I don't know if I have the patience to write a book all the time.
So before we get into what happens if we can achieve net zero, and we'll get to what definition of that is in a moment. How did you get to being a professor of climate science at ANU? I mean, they didn't just sort of say, oh, you got born the other day, here you are, here's your pathway. So how did you go down that pathway?
So I just remember being in geography in high school and learning about the Kyoto Protocol, learning about weather, learning about carbon. And, back then there was a little bit more hope that we could get this sorted a little bit sooner.
I remember Kyoto was so hopeful.
It was. And, it just showed we could all get together, make an important decision and make change, right? It was very, of course we can do this.
Because we did it with the CFCs.
Chlorofluorocarbons. And the ozone hole. So, of course we can do this, right?
We could have done it.
We could have done it. And we can still do it.
That's a message of hope. We're being positive here.
There's never not a reason not to have hope. But anyway, and I went into studied atmospheric science at uni.
Oh, really?
And
where at?
Macquarie University in Sydney.
In Sydney,
I grew up in Sydney.
Yeah, okay, and then?
And just started doing a PhD at UNSW Sydney. There's a big climate research centre there. and got a PhD looking at extreme events. And yeah, just one thing led to another. I really enjoy what I do. I really find extreme events fascinating. I tend to study extreme heat mostly and health impacts of extreme heat. And I like what I do because it's interesting, it's always developing, and it has meaning to the real world.
So how do you get from a PhD to becoming a professor? Because in Australia, they don't give away professorships lightly.
No,
it's
that's
a serious
true.
thing.
A bit of luck and a lot of hard work.
A lot of hard.
Yeah.
It is amazing that hard work is necessary, but luck helps a little bit now and then.
Right. So the reason why I've got the job I've got now, well, there was a position open, and I asked if I could maybe take up a professorship, and they said, "Yep, that's fine." And so I was lucky enough to get that promotion at the right time. So that's where the luck came in. But previous to that, it was hard work. 2 postdoctorates. A whole lot of soft money on ARC research grants, and just hanging in there, but also realising at some point if things don't work out, well, that's just sometimes the nature of the beast.
Now, one question that comes into me on the radio in the science communication thing is, surely the heat of global warming comes from just burning the fossil fuels, and the answer is no, it comes from the carbon dioxide acting like a one-way valve.
Well, basically, yeah. So carbon dioxide. Yeah. So the way I've explained it before is like carbon dioxide's like a blanket, right?
Yep.
The thicker the blanket you have on yourself, the more heat it traps coming off your body. It keeps you warmer and more snug. Carbon dioxide's like that for the planet. We need a little bit, and we've had that for a very long time to keep temperatures at, livable levels. But too much is bad. Too thick a blanket is bad. And what carbon dioxide does is just absorb a very small amount of a long wave band. And that's what comes off the surface of the Earth. And it does that at certain temperatures where it sits high up in the atmosphere. It doesn't do that. It doesn't act as a greenhouse gas on the surface of the Earth. It's up in the atmosphere.
The sun is emitting basically half of its output, 1 watt per square metre when the sun's directly overhead, half as heat roughly and half as light. And then the light comes through okay, and the heat comes through because it's coming through at 5,500 degrees, which is the temperature of the surface of the sun. So the greenhouse gases don't see it on the way down.
No, they don't see it on the way down. It's too short a wavelength.
But
it's
then
coming up.
It warms the ground to 15 degrees C, roughly, ballpark figure.
Well, it absorbs the long wave radiation, and that goes back up into the atmosphere.
So now the ground is radiating up.
Exactly.
So
exactly.
Now we're having the second chance for heat to kiss the greenhouse molecules.
Exactly.
They didn't see it on the way down at 5,500, but they do see it at 15 degrees C, and they absorb it.
Yeah, well, and they absorb it. They hang on to it for a little bit longer, right? Because it just kind of like the wavelengths will bounce off all the carbon molecules, or any greenhouse gas for that matter, and it keeps it just in the atmosphere for a bit longer. But the problem with carbon dioxide is it hangs around for hundreds of years. It's not like, we emit it today, it's gone tomorrow, or next year, or even in a decade or two. It's there for hundreds of years.
And this is part of your research with regard to what happens to the climate after we get to net zero.
Yeah, that's right.
The figure I've heard is that the amount of heat trapped each day by the carbon dioxide molecule, so the heat comes down, warms up the ground, doesn't see the greenhouse, hits the greenhouse molecule, and there's a carbon dioxide molecule in the atmosphere, and then it absorbs the heat, and then half of it goes into space, and if it all went into space, there'd be no troubles, but half of it goes down to the ground.
In the lower part of the atmosphere where we feel the weather.
And so that's rough. I've heard the figure 600,000 Hiroshima bombs of heat per day.
It changes. It keeps going up and up. But
unfortunately, it keeps going up.
Yeah.
And you can get away with that for a day or a week.
But
or a month,
and it goes
or a
up.
year, or a decade, but many decades you just can't do that. And so the heat has just been building up. And you were saying you're dealing with heat. I was totally surprised when I think it was on the 4th of January in the year 2000, Sydney was the hottest place on planet Earth. In Penrith, 48 degrees or something.
We've had, so in 2020, it was 48.9 out in Penrith, or 48 point something. But it was the hottest place on Earth.
So boring old Australia, unlike the Middle East or somewhere where you'd expect, became the hottest.
Well, to be fair, in the Middle East at that time of year, they're in their winter.
Right.
So it does get hotter there, definitely.
But if you'd said to me when I was growing up that one day, thanks to global warming, Sydney will be the hottest place on Earth for one day, I would say that's impossible.
I would have too. But now I don't. Now obviously that's possible. I used to live actually out in Western Sydney, and I did it around that time. And I had a friend of mine that heat wave was well forecast, and they were talking to me about how hot it would be. And they're like, do you think Sydney will reach 50 degrees by, 20, I think maybe it was 2040 or 2050. I said, no, that's not going to happen. And after that day, I've changed my answer.
Well, and also I think around the time we had the big fires, something like 1/5 of all the trees on the east coast of Australia caught on fire.
Yeah, it was some ridiculous statistic, and it was a very intense fires as well, just because of how dry everything was.
And we had these, what do you call them,
Pyrocumulonimbus. So fun
Can
fact.
you talk about them?
Yeah, I can a little bit. In that season alone, 2019-2020, we doubled the number of pyrocumulonimbus fires on our long-term record. So I can't remember the exact numbers, but say we had 100 total. In that season alone, we went up to 200 total.
So we're talking about a fire that punches up through
Yes.
higher than Everest, higher than the aeroplanes fly.
Yes, correct. So all of the weather happens in roughly the first 10 kilometres of the atmosphere, or the 10 kilometres above the surface of the Earth. And when you get thunderstorms, you get big convection clouds that go all the way up the top. And a pyrocumulonimbus does that, but it's made out of bushfire smoke. So it's not like your big fluffy white clouds that bring storms. It's a big fat bushfire cloud. It can create lightning, and then it can create more fires ahead of the fire front by that dry lightning. And they're very dangerous. You don't want to run into one. You don't want to fight one. Well, basically, you can't fight one. And you just want to prevent that condition from happening. But as the climate's getting worse, we're seeing more of these fires occur because basically the weather is primed for them.
Which we have changed.
Yes,
yes. So I remember reading an article in Nature in Science, and it said something like the first pyrocumulonimbus was discovered in 1977.
Okay.
And there'd been a small number of them, and suddenly the number doubled due to the Australian bushfires.
Yes, exactly.
And it's of the order of 100 for the whole planet over like several decades.
Yes.
And they cooled down part of the atmosphere leading off to the triple La Ninas, they were saying.
Yeah. That was really interesting, that science was, the smoke that came off it, because the smoke then stops for a little bit. It stops shortwave radiation coming in from the sun, like the aerosols, like little particles. And that would have helped cool and potentially helped feed the 3 La Ninas we had in a row.
I've seen the satellite photos, and you can see that the southern hemisphere starts off with white clouds, and over a period of 3 days, the entire southern hemisphere about 5 days, goes to brown clouds. The smoke from Australia covered the entire. Any clouds started going dark.
And it's even started to layer in the glacier. Well, it laid in the glaciers in New Zealand.
Really?
It blew over and settled there as well. Yeah.
Wow.
Yeah, I know. It was a very, very sobering and heartbreaking year, that one.
Okay, but we're still optimistic we can stop it.
Oh, yes.
Okay.
No, we are. Yeah. Now, there's always hope.
So the figure today, roughly ballpark figure, is that each year we're chucking into the atmosphere around 37-ish, 40 billion tonnes of carbon dioxide. And the figure I've read is that trees could absorb about 5 or 6 of that.
Yep.
And we're overloading what the natural sinks.
Yeah, so trees are great. Like we all need more trees.
We need more trees.
Done a bad job of preserving our trees in the past, and they do work as a sink, provided they don't catch the light. We want that carbon to come down and stay down. And unfortunately, that doesn't always happen as we'd like it to.
On a separate issue, I once went to a lunchtime talk, and one of Australia's multi-billionaires who's a land developer said that he was really sorry he hadn't managed to get rid of all the trees in Sydney. Okay, let's just move right along.
Pill to swallow, yep.
Okay, so climate after net zero.
Yes.
So the solution to getting net zero is ridiculously simple, which is simply 6 words: keep fossil carbon in the ground.
Yes, correct.
And 6 words. And we're using fossil carbon 60% for energy, 20% for agriculture, and 20% for microplastics, which is why you and I have microplastics in our brain.
Yep.
And all of those things can be done without fossil carbon. So let's assume that we're heading towards net zero, and the sinks are gradually pulling it down, and we've increased the carbon dioxide level by basically 50% since pre-industrial, from 280. We've had another 40 to that, 140, and it's up around 420-ish, something like that. So what have you been finding in your research?
So what we usually do to understand future climate is run physical climate models to simulate what conditions might be, because we don't have a crystal ball. These are our best tools to see what could happen. And we used to run them with various amounts of greenhouse gases. So what if we did business as usual, or suddenly sucked all the carbon out of the atmosphere, or everything in between? And that would give us a glimpse of what we can expect in the future.
Yep.
But only recently we've started to do that when we stop emitting carbon dioxide. So we basically say, at this year, we will stop emitting carbon dioxide versus this year. So it's more of a, let's flick off the switch, let's all stop burning fossil carbon, and then let's see what happens with the climate. And some of the simulations that I've looked at have done this for 1,000 years. And it's basically stopped emitting carbon at 2030 every 5 years to 2060. And then we've just kind of, it's basically a what if. What if, we did this, what would the climate look like? And we've been able to look at this globally. So it's a global climate model simulation. These take
What a
months
huge
to
amount
run.
of work that must have been.
So I didn't personally run the models. This came out of research from the University of Melbourne and CSIRO.
They must have worked so hard to do
They
that.
would have, yeah. A lot of planning and a lot of computational power goes into running these climate models. It's absolutely essential. And so we basically went, right, well, we've got these simulations, let's pull them apart. So one of my colleagues, Andrew King at the University of Melbourne, basically took a global snapshot. So what happens with Antarctic sea ice, what happens with average temperature, what happens with rainfall for these different time periods. And then I've gone on to look at, what happens to heat waves across the world? Because we all think, and rightly so, we fundamentally need to stop emitting carbon dioxide and other greenhouse gases. That has to stop. There's no argument there.
Well, the politicians who have power might argue, but the scientists are quite
There's
clear.
no argument there.
There's no argument with the scientists.
Yes, no, the science doesn't lie. Facts
The science
don't
doesn't
lie.
lie.
But I think, and I've been guilty of this too. We're like, we'll get to net zero and everything will be better. It will be all right. We've just got to get to net zero. But what these simulations show us is it doesn't necessarily get better. It may not get worse, but it doesn't get better. So, for example, if we're looking at heat waves over North America, they, the later we leave net zero, the worse they become in the future.
Right.
But they kind of level out. They don't decline.
They don't go back.
They don't go back, but they kind of level out a bit. But over Australia, they keep going up and up and up. They don't go up as fast as what they're doing now, but it's still significant over that 1,000-year period. And we think that's because what this climate model simulation does is the Southern Ocean absorbs a lot of heat. Now, whether or not that's true, we can't verify because we don't have enough data to say, yep, this is the speed at which the Southern Ocean absorbs heat. But physically, it's highly plausible because the ocean absorbs over 90% of the heat that carbon dioxide, keeps in the atmosphere.
600,000 Hiroshima bombs per day.
Yeah. So it's a huge amount. We'd be roasted now without the ocean, effectively. And it works at a much slower time pace than the atmosphere. It's, the way it reaches equilibrium and moves around is much, much, much slower. So it's plausible that the Southern Ocean will just continue to absorb heat for, a few hundred years to millennium, perhaps longer. It's just, we just can't measure that. We just don't know for certain, but it does make sense.
But what about using, in addition to natural sinks, artificial sinks and bringing the carbon dioxide so it's gone 280 and then add another 50% to bring it up to 420-ish? What if we bring it back down again? Is that, have you looked at that, or have you just left the carbon dioxide in your models at 420?
In these simulations, it's just been left.
At 420?
At 420, or it depends. So at 2030, when we looked at the 2030 run, so, we reached net zero at 2030, it's whatever was predicted.
Right.
And then it goes all the way up to 2060. So the longer you leave these simulations, the more carbon dioxide stays in the atmosphere, the more that there's there. Some simulations, not the ones that we've run, but some simulations look at what happens when you draw out carbon artificially.
Yep.
And that does see a temperature decline at some point. But there's uncertainty. I hate that term. I probably shouldn't use that term. But we're not entirely sure when exactly that might happen.
Sure. Because the drawdown.org people in the USA,
Project Drawdown.
Yeah. They discuss different types of sinks. And that would be good. Now one thing I should just get out of the way.
Yeah.
We're not heating up the whole Earth. We're only heating up the biosphere where we happen to live, which is the bottom. Is this right? The bottom 10 kilometres of the atmosphere,
yeah. So the
top kilometre of the ocean.
The troposphere. Yeah. So that's basically the part of the atmosphere where all the weather happens. So that's where we live.
Yeah. So being specifically accurate, we're not heating up the centre of the Earth. Or,
no.
Or 20 kilometres down.
Literally the surface.
But unfortunately, we happen to live there. We're heating up the bit where we live.
Yeah.
So are you kind of optimistic long term?
This is a good question. I'm asked this question a lot and I still haven't formulated a really good answer. I guess there's never a reason not to have hope. Things that have been happening lately, not just in how lax we've been taking this problem, but also global politics points to things not happening as fast as they could. And we're measuring that. But whether or not we can limit global warming to 1.5 or 2 degrees Celsius or 3 or 4 degrees Celsius, there's never a reason not to do anything and not to have hope.
Right, because
So-
people do say, for example, why should Australia do anything because we're only a small percentage of the world?
Funny that you say that. I've
Yeah.
got a statistic. So we're
Lay
roughly
it on me.
1%.
Yeah.
But we're still in the top 20 of highest emitting countries at that 1%.
And it's like saying in the Second World War, well, we're only a small country.
Exactly.
Why should we go into the effort against
Every little bit-
Nazi Germany?
Well, every little bit counts. The IPCC, the Intergovernmental Panel on Climate Change, literally say every tonne of carbon dioxide counts. And yeah, we can't take that defeat as attitude.
Okay, now we're just winding up here. How can people follow you in your fine work, or even become your PhD student or undergraduate student?
Absolutely. So I'm based at the Fenner School of Environment and Society.
Fenner?
Yep.
Fenner. Now, he was my mum's smallpox man.
He was, but he also had a soft spot for environmental science.
You're kidding?
No. So that's the school. Like everyone kind of does a double check.
So he was part of the thing that brought us the fact that in the last 1,000 years, 10% of everybody who died on planet Earth died from smallpox.
Yeah, right.
And he was part of the team
Yeah.
that eradicated smallpox.
Yeah.
And so you're at the Fenner, so that dear audience, remember that, Fenner School
Yep.
of...
Environment and Society.
Okay, so they can find you there
Yes,
at
correct.
Australian National University, and
Yes.
you
And
take on students?
I'm also, so I've got a full team at the moment, but I'm always happy to talk to upcoming students. I also work closely with the Centre of Excellence for 21st Century Weather. So we're researching how weather and climate change in the face of climate change, net zero or not. And we also have a podcast now called Totally Cooked, where we talk about weather and climate as well.
And going fully hip, how can people follow you on social media?
Oh, that's a great question. I'm on LinkedIn. What am I? I'm Sarah in Science on Blue Sky.
Is Sarah?
Yep, Sarah in Science, all one word.
Sarah.
Correct. Thank you for
In
checking.
Science.
Yep. And that's on Blue Sky.
Oh, that's on Blue Sky, yep.
So the podcast is on basically everywhere you get podcasts from, and that's Totally Cooked. But we also
Totally Cooked.
Totally Cooked, yep.
Totally Cooked, yep.
Yep, Totally Cooked, the Climate and Weather podcast. And then we also have handles on social media, 21 Century Weather on Instagram and TikTok. 21 Century Weather is also on LinkedIn, and I'm also on LinkedIn too. If you just put like Sarah Perkins-Kirkpatrick into LinkedIn, I think I'm the only one.
Look, thank you so much for coming on and for trying to make the world a better place.
Thank you for having me. I really enjoyed it.
Thank you, Professor Sarah. Shirtloads of Science is washed, spun and aired by the University of Sydney.